Okay, so my name is João Acabado. I work as a principal SRE at Sky. So it's really great to be here. So thanks to all the community, to the organizers, to the everyone else presenting. Keep doing it. Yeah, I think it's great. So today I'll be presenting powering resiliency. So I believe we should all agree that we should be failing in favor of the customer. So whenever we fail, we just demonstrated that. So, and I had a really good fallback, which was doing the other presentation. So for us to do this, I believe we need to be effectively using our fallback. And I think the example we just did was really great because Sergio was very quick on the trigger. So the timeout was very short. So we moved to the next presentation very quickly. And I think this is a great example of this. So to effectively use our fallbacks, we actually need to be triggering our failure mods before disaster happens. And to illustrate that, let's get to North London on the afternoon of the 9th of August, 2019. So at this time of the day, there was a storm happening. It's UK things, right? On 9th of August, there was a storm happening and lightning struck the power grid between London and Cambridge, more or less. And this led to a sequence of events that will be going through. And I think that it's very interesting to illustrate the limits of the systems and how can we protect our end user. So there are two special places to mention. So one is the Orange Sea. It's a near shore wind farm. So it's a wind farm out on the sea. And then there is the Little Barford, which is a power plant with a gas turbine, well, with a steam turbine and two gas turbines. So what happens here? So around this time, so first thing to be said, I don't know much about electricity, just maybe the really basics. But what happens is an idea we borrowed from the electrical engineers are the circuit breakers. So whenever there isn't any disturbance, any problem on a circuit system, a circuit breaker opens so that it stabilizes, and once it closes again, it can then be I just noticed I have this on front of you. So when it closes, then it can stabilize and the transmission can keep happening. So on that, what is interesting is what happened after the lightning struck the circuit grid. So right away, it was very quickly, a matter of milliseconds, that segment of lines closed and opened and closed very quickly. But afterwards, there was a phase shift which was sent throughout all the power grid. So first to the wind farm on the sea. This is the Orange Sea loss. So we can see more than 700 milliwatts of generation lost. After this, the steam turbine on Little Barford also was the protection systems triggered, and there was the loss of around 250 milliwatts. So that was just the beginning. Afterwards, the loss of mains. So these 500 milliwatts, this corresponds to the micro generation, so embedded generation throughout homes and different places. So that's distributed around that region. These were also lost. All of these triggered a variation in the frequency response. So whenever this happens, there are systems in place there is reserve generation in place to be triggered to try to stabilize the system and then to recover it. So that's what we see around here. And so the reserve generation triggered and kicked in. But then real tragedy happened, at least in terms of systems engineer. And this was, so the other two turbines on Little Barford, so there is a steam turbine and then two gas turbines. What happens is that the gas turbines are connected to the steam turbine. So the way they cool is by sending the steam so the gas turbines heat and produce power, and they send the steam to the steam turbine. Given that the steam turbine was non-functional and was closed, they started overheating, and then in a cascading failure, so the first was triggered automatically and stopped working, and then the second was also triggered, and this made the frequency reach a threshold. So around this threshold of 48.8 Hz, the whole circuit breaker for this region triggered, and around 5% of the customers lost power on this zone. So here, I think here we can see a couple of things. So the different limits, the recovery systems, and how failures can be isolated in a way, but can also propagate to other systems. So this is what happens in a power grid. Let's try to think about this on our system. So your risks will vary, right? So depending on what you do, you will have different modes of failures. You'll have different modes of testing. We just saw my Zoom failed. So I'll be focusing here on HTTP APIs, so that's where I've mostly applied this. So what I have here might be known to some. So this is Little's law, which says that the load in a system is equals to the average rate of arrival to that system, and the work done there, or the length of time of an item throughout the system. So this can be applied to almost everything, from traffic to HTTP APIs to event-driven systems. Usually what we do on HTTP API systems, so on backend services that have APIs, is we do load testing to try to understand the limits of the system and how well it performs or not. We can do resilience testing to see how it works when something fails. We can also test different ways of scaling if there's any bottleneck, if there's anything in common between these. So what else can also we do? And that's where we'll get. So where will you be when your system gets overloaded? So this is one of the points, and here I illustrate what happens when a given system gets over its capacity. So on the first graph, what you can see, so you can see a trigger on capacity when we went above our capacity. And what happens here is that once we get above our capacity, according to Little's law, our latency, or the time that each event or each item needs to get through the system, will increase. And it will increase until the point of complete rupture. So when all of our buffers, so this happens depending on the capacity of our system in terms of buffers. And when this happens, most of the times the behavior is unpredictable. So what we are seeing here is, if somehow you are able to limit and to reject anything above your capacity, you will have a much more controlled behavior, and your system will be able to work in a predictive way around its limits. So being prepared to fail. So there's another good reason. So not only to avoid a big disaster, but there's also a good reason to set your limit, not only in terms of capacity, but also in terms of timeout. So you can have a good fallback. And what I mean by this is, imagining an HTTP API, you can have some dummy response that you always return whenever you can get a fresh response. Another thing you can do is you can have a proxy in front of you, and that proxy can return a cached response in case it doesn't get the fresh response. So that's what we have illustrated here on this image, and basically it shows how to have a fallback in proper time. We need first to time out. Another dimension where these kinds of limits are very important is that if we don't define the limits of our system, and if we don't contain some kind of failure, there's always the risk that failure will propagate throughout systems. So if our system is unpredictable, or if it might have a behavior that we don't know, we can't exactly set up expectations on, the chances of it breaking other systems upstream and downstream are much bigger, and it makes the whole platform much more unpredictable. So on top of this, I have here a checklist. And so the first two advices will be that for each service, we should always have the maximum throughput and the maximum latency. So this should be done by first understanding the dynamics of our system. This can be, so the throughput, of course, it needs to be done with proper NFT testing, with proper load testing in the different conditions. So there's also some variance in behavior, and the latency, it should be seen according to these load tests, but also in terms of expectations of our clients or consumers. So in our case here, so we wouldn't want to expect 5 minutes to get between each talk. That's the example I'm doing. But in a service, you might find unacceptable to have a response longer than 1 second, or taking longer than 1 second. So you should have maybe a timeout at 800 milliseconds, and try to use our fallback right after that, because it will still some time. With this, we should be able to implement protection mechanisms. What does this mean? So this allows us to have API rate limiting. So this can be done in the services themselves, but usually when you have loads or different instances, or multiple nodes to support your service, you want to do this in a central point. So it could be a service mesh, it could be a proxy, some kind of ingress controller in a cluster. The other thing to do is to have timeouts and fallbacks to make this work well. So the last thing I wanted to say was around the example that I went through before of the UK power grid. So in the end, the power grid was just down for it was less than 30 minutes, and the biggest problem they had was in the trains. So there were the trains are also connected to the power grid, and some trains shut down. They were able to recover most of them. The problem was in some of them, they were rolling out new software, and there was no way of restarting that software without the intervention of the technicals. So this is just another example of being prepared for the worst is a very good thing. And I think even in the big scheme of things, the failure of the power grid, it's a good example of how can things fail orderly and under control. And that's all.